Welcome everybody to the fifth technical lecture from IF NCTS. The faculty for today is Dr. Gyanamurthy, who is having over 40 years of experience in all aspects of foundry, from pattern making to project management. He was a former director and council member of Casting Technology UK, formerly known as BCIRA. He is an advisor to McKinsey and many other global consultants, and several academic institutes and major casting users are seeking guidance from him regularly. I invite Dr. Gyanamurthy for his lecture. Thank you.
Thank you, dear Satish, for the introduction. And good evening to all the participants here. Some of you might have been here last Friday, and others might have joined only now. Anyway, good evening. And I'm not able to see the list of participants. If there are some familiar figures here, good evening and welcome to you all. Okay, let me go on presentation. Yeah, last time we went through the gating system or the flow of liquid metal into the mold, and we handled both the theoretical portion as well as the practical portions of that on last Friday. Let us get into the solidification and feeding of castings this time. Now, education is not the learning of facts, but the training of the mind to think. This is what Albert Einstein said. It's a very far-reaching and groundbreaking statement, because many of us, especially the practical foundrymen like us, in fact, I emphasize this point whenever there is an opportunity, we settle down on, let us say, okay, these are the facts. How much of carbon you must put? So much. What happens if the carbon is more? In the case of iron, it becomes soft. In the case of steel, it becomes hard. We stop at that. So it is the learning of facts. Now, with the Google, it has become very simple. You don't have to go to a library. You don't have to do any reading of books. You don't have to search into the shelves. It's available. But the training of the mind to think is the true learning or the true education as per Einstein. And we can't agree with him more than that, because we have seen in our own cases that the facts and assimilating of facts and keeping the facts in the mind do not seem to help us in the long run. It's only when we know how things work, we seem to be progressing further. Casting is about melting metal and pouring to desired shapes. Heating and cooling, and hence heat transfer, plays a major role in foundry business. Presently, we have simulation softwares, and by touching a few buttons, we get results of how casting solidifies in a given situation of mold. It may be interesting to know a little more about what happens behind the computer screen. Satish, just for an interruption, are you able to hear me?
Yeah. Yes, sir.
Okay, fine. Let me go through that. Now, I have traveled quite a bit in India and in many parts of the world. Now, in many foundries I visited, I won't blame the top management who is busy trying to make the two ends meet and make a decent profit, if at all it's possible in foundry business, which I know is very difficult. But go down to the technical people. If you talk about solidification or simulation, they know what button to press. Many of them may not know what maths goes behind it or what theory goes behind it. I have been repeatedly telling over a period of time, and whenever there is an opportunity, I stress on this point, that we should know a little more on what happens behind the screen. How heat is transferred from one place to another within solidifying metal and then into mold, and then from mole to atmosphere, and how shrinkage is formed or eliminated make a very interesting study. When liquid metal cools, it's governed by conduction heat transfer. Now, solidification is a phenomenon of change of state from liquid to solid. This leads to cavity known as macro or micro shrinkage. Let's go into the top one. Solidification is a phenomenon of change of state from liquid to solid. When a well-lit group of friends, let's say, sit in a air-conditioned room, this is an analogy I'm giving, they may be pretty close to each other, talking and gesticulating. If you switch off the AC, they would each need more space around them and feel agitated and could be jostling about their seats. If the room gets hotter, they tend to get up from their set seats and move around, but still within the room. If the room gets much hotter, the bond is more or less lost, and all of them go about freely out of the room, in fact, if it's possible. Now, this is precisely what happens when you heat a piece of solid metal. Molecules within a solid are attracted by intermolecular forces and remain in their place, though vibrating about their mean place. The vibration being proportional to the energy content of and represents temperature. When you give energy to anything, it has to reflect in a particular way. In this case, they vibrate, they move around uh, about that mean place, and that's called temperature. If you apply heat, the molecules vibrate more, which is demonstrated by increase in temperature. And at some level, the bond breaks down and they move about freely. The changeover is called phase transformation from solid to liquid. This requires a quantum increase in energy called latent heat. Technically, it is defined that at the point of latent heat, there is no change in temperature, theoretically in pure metals, but there is. In pure metal, there is no increase in temperature, but in other things, there is a change. Now, when this happens, it leads to shrinkage cavity. The overall volume occupied by the molecules have to increase because they need room for movement. So, in simple terms, liquids have more volume for a given weight or number of molecules. On the reverse, there is contraction when liquids cool to solid. While there are exceptions like plain water, gallium, bismuth, etc., most pure metals contract on solidification. These exceptions require special deliberations, which we may not be done here. We'll also not discuss about a gaseous state where the molecules break away from liquid, like guys moving out of very hot room. We don't discuss about it here. While talking of alloys, plain cast iron expands and may almost compensate liquid contraction, which we shall discuss later, along with shrinkages arising out of liquid metals solidifying in all other cases. Now, when we talk about pure iron and steel, which is relatively low carbon content, they contract on solidification. Whereas cast irons, which is higher carbon, expands on solidification. Well, on solidification, carbon, which has much smaller atomic radius than iron, can conveniently find shelter in interstices. What we mean is gap between atoms of iron atoms up to a limit. For example, if you arrange the coins in a carom board, 19 coins, you can always take a small pepper or a small pea and you can put them between the spaces. They are called interstices. That's what carbon sits in iron atoms. When they come out, however, They join together and occupy their own space as graphite. This increases overall volume or counters to some extent the otherwise contraction of pure iron. Now, the overall effect being expansion instead of contraction, especially when carbon content is high. Well, it may be interesting to note that when atomic radii are same or pretty close, there is total miscibility of metals like copper nickel in monols or gold and copper, which has given the biggest problem to the what you call jewelers over a period of time, which we brought in Archimedes, which we will not discuss here. Well, the physics of solidification. It's hard to believe there is no mathematical formula, however complex, to calculate time it takes for a glass of water to solidify in a refrigerator. We do have a set of nonlinear differential equations, initial and boundary conditions, and a host of empirical, semi-empirical, and approximate solutions besides. Finite analysis to give somewhat close answers, but not the answer as mathematicians may wish to see. Well, let's come down to earth. What's our goal now? Push the defect. We are not talking about any defect here. We are talking about the shrinkage defect in this particular case. Push the defect out of the casting. Push the defect to a place where it does not matter. Okay, like a riser. Now let's talk about the function of feeders and what they do. So in a lighter vein, risers supply hot metal to castings, not at the mouth or gate, but on the wrong end. Pardon me. Now what are the requirements of risers? Most importantly, it should be in liquid state longer than the hot spot to be fed. It should solidify later. For example, you should be able to, well, it should be in a liquid state longer than the hot spot to be fed, correct? It should solidify later. In short, it has more volume to surface area ratio, that is called modulus, than the hot spot. Now let us discuss a little bit on what is modulus. If you take any cube or any sphere, the heat content is in the central body, which is the volume. In the case of in the case of cube, it is L cube. In the case of sphere, it is 4 by 3 pi r cube. That's where the heat. Where is the loss of heat? Is in the surface. In the case of cube, it is 6 times the area of each side, 6 L square, or 4 pi r square in the case of sphere. Now, you lose heat through the surface, and heat is conserved in the central body. For example, if you put a piece of ice in a water, all the people who drink or who have experience in this line know if you want dissolution of ice to be faster, you break the ice into pieces. Suppose you break the ice into 8 pieces. Now the total volume remains same. So the amount of heat which was there remains the same. It is not changing. But the surface area is increased because on every broken surface, you have more area now. And heat transfer is through the surface. And over a period of time, the ice solidifies, sort of dissolves much faster. The reverse also takes place on solidification. Right. Now, let's get into the next area. So, what is the requirement of a riser? Or, like, let us say, go through what John Campbell talks about the 7 feeding rules of a riser. Do not feed unless absolutely necessary. For example, many grain foundrymen you would see providing risers where it is really not necessary. In the case of ductile iron, people with experience in ductile iron would confirm that when you pour a casting and come near the riser top after some time, you will see worm like liquid metal coming out of small cracks in the riser top on the solidified metal. So that means there is an expansion of ductile iron, and you have not made the choke, or let us say the riser neck, small enough or good enough. So it comes through the riser. Imagine a situation where you have contained that expansion of liquid metal in the case of ductile iron by reducing the neck area. You would have so much of better feeding. So this is what John Campbell says: do not feed when it is not necessary. Well, that is rule number one. Okay. In the case of steel, of course, you require a lot of feeding. Feeder should solidify later than casting. Obvious. Okay. Somebody who gives should have more liquid money than the person who is receiving it. Feeder should solidify later than casting. The feeder must contain sufficient liquid to meet the volume requirement. The analogy is simple. Now, if you want to give somebody money in order to improve their status, you should have more money. I mean, in the obvious sense, there are a lot of people, ethical people, who give money or give resources even if they have much less. Let's not talk about it. In any natural phenomenon, things go from higher level to lower level. So, when you have to feed or when you have to give something to somebody else, okay, you should not solidify yourself and you should be open, and hence the riser should solidify later. The second one, feeder should solidify later than the casting, is what we said. The feeder must contain sufficient liquid metal. It should have enough money to give, or the feeder should have enough liquid metal to be given. Now, the feeder must contain sufficient liquid to meet the volume contraction requirement of the casting. Now, it's a bit tricky. Suppose the volumetric shrinkage of a casting is, let's say, 9%. Okay. Now, suppose you are giving a riser of volume R, the casting is volume C. Now, casting plus riser both require a 9% of liquid metal for feeding. So, C plus R into 9% should be fed by the riser. And the riser multiplied by the riser efficiency, which is 30% or 40% or whatever it is, should be able to feed both the casting and riser. In a very simple case, if the casting shrinkage is 9, and if the let's say the riser shrinkage is also 9, totally it's 18%. Your riser should be able to give at least 18% of itself in volume. Okay, so this is what is very important. Then John Campbell talks about pressure matching and whatnot. Okay, let's not go into that. Let us skip that. Okay, now feeders. Casting demands feed metal for soundness, and the feeder itself has to be correctly dimension position. You have the heat transfer criterion, as we said. Then we have the volume criterion, as we said. And we have the directional solidification criterion. Let's elaborate on all this. We'll go into a little more on the analytical part of it a little later. Heat transfer criterion is, let us say, the same as directional solidification criterion. When castings solidify, I said, the volume decreases and then there's a shrinkage. Unfortunately, in life, it does not happen in the very center of the casting or in a place which is convenient for you to predict. Now, the skin starts solidifying because that is nearest to the heat transfer. And then the shrinkage, let's say, it keeps on moving towards the place which is lost to solidify. This is the heat transfer criterion, which we'll discuss a little later. Volume criterion is what we said earlier in the previous John Campbell's list. Volume criterion is you should have enough volume of liquid metal. In addition to dimension feeders, chills, insulating, and exothermic sleeves are used. We'll go into each one of them a little later. It's hence necessary to predict heat transfer, including phase transformation, in such a three-dimensional field comprising of metal, mold, sleeve, chill, and atmosphere in all its complexity. In the earlier days, before the advent of simulation software, I would say before the advent of even mathematics for understanding the simulation, we had a set of, I won't say thumb rules, experienced, oversimplified statements. One is called the Shorinov rule, which says that time of solidification in any condition is proportional to volume by surface area, V by S A. This is what we said. You break an ice, it melts easier. Same as the solidification, you give more surface area, it solidifies faster. So, for example, you take a 100 kilogram casting. One is a very chunky volume, let us say L into B into H, they're all same. Another, take a thin walled casting, both are 100 kg. You definitely find that the second one solidifies faster because it has got a lot more surface area for the 100 kilograms volume. Okay, or T is proportional to V by SA. Okay, now the N is root 2. One can try to argue on that. Now, the another one is called mass transfer requirement, which we just now discussed. Okay, that is the volumetric shrinkage which is possible or volumetric liquid metal available in a riser should be equivalent to alpha, the contraction of the volume of feeder plus volume of riser. Now, the other one is the feed path requirement, directional solidification towards the feeder. That is, if you have a hot spot and then adjoining, let us say a few centimeters, you've got another hot spot. If the two are not linked by sufficient hot spot, you can never feed both. So you have to do some sort of a trick to reduce the hot spot of one, okay, in order that that solidifies a little earlier than the second one, and there is a feed metal path. We'll come to another picture by an author, John Campbell, again in this case a little later. Okay. Pressure requirement also we'll talk about a little later. So what are the techniques which are available? Several factors which govern relative freezing time, like volume to surface area ratios, have been developed in the past. That's what we went through now. Classical solution involves mathematics and it's available only for the simplest of geometry. In fact, on the last lecture on 8th, when you're talking about the flow of liquid metal, we discuss quite elaborately on this, that classical solutions, they depend on very complex mathematics by people who are familiar with in the academic circle or who are in touch with academics in spite of being foundrymen. They would remember the famous book Radl, Karslan Diega, and Arpasi from Israel. These are very fine books. So they define on the various methods of solving this differential equations. See, what happens is, unfortunately, in nature, you have always a set of things which tell you what's happening. They're all by equations. Now you have to sit back and try to solve these equations and try to find out exactly what is the situation and what is. For example, last time, in fact, I told you a case that when you drop a stone, okay, after some time, it reaches a lower level. We all know that S is equal to half gt square. It travels by, let us say, 5 meters in 1 second, or 32 feet in 1 second. It reaches. Now, are we not assuming in this that gravitation, which is 9.8 meters square per centimeter, or whatever it is, that is a constant. Right? We are assuming it is constant. But we know that G is not constant. G increases as you go towards the center of the earth or it increases. Now, when you try to solve this, it becomes a very complex nonlinear equation. Now, what is the nonlinear equation? Now, you are trying to find the height of fall. Okay. But the height of fall itself depends on the time. So this becomes what is called, suppose you want to go from here to the railway station. It depends on so many factors. One such factor is, let us say, the condition of your car. The next is your mood, and then let us say your uh, climate of the day, weather of the day. If you give equal proportion, 33% on the car condition, 33% on your mood, and 33% on, let us say, the weather. Now, if your mood itself depends on whether you are traveling faster or less, so the time t you said depends on these three factors, but the mood again depends on time t. You get the point? So these are called nonlinear equations. And you get differential equations and partial differential equations when you want to deal with only one variable. Now, the complete heat transfer is full of such kind of anomalies, and we are trying to solve this. Now, when you try to solve this, we need to know certain properties of metal and mold. Now, thermal conductivity K, specific heat C, density of metal R for liquid and solid, and hence thermal diffusibility, which is called K by RC. The above four for liquid and solid, and latent heat L. Now, the same thing you require for the molding material. Thermal conductivity, specific heat, and density. Now, the biggest problem in simulation software is data is not available. For example, data is not available for the various things for various liquid metals, especially thermal conductivity K and specific heat C at different temperatures you do not have. Now, people, when they do research on this field, as what I did myself 3 decades back, we try to get the data, but the literature is full of vacuum because nobody has done research on all these fields in order to find these data. There are certain universities, one Dr. Pehelke from University of Michigan, Ann Arbor, he pioneered this work and tried to collect all this data, but finally they were not able to get it. And the molding material, same is the problem with the riser sleeves and all that. We don't get it. Okay. The initial conditions are pouring temperature, non-isothermal conditions, molded temperatures, and whatnot. I don't want to threaten you with this equation, and let us try to give the practical aspect of this equation, what it simply means. Okay. Now, it simply means that heat moves from higher temperature to lower temperature. In other words, temperature gradient is important for heat transfer, right? At any point of time, the sum of what a tiny piece of material gets from or lose to neighboring points leads to increase or decrease in temperature. Okay, to involve. Let's give an analogy. Let's say a group of people, we are all sitting in a room with different stuffing of currency in our packets. We have different amount of money, but we are all sitting in a room. In the usual days, not the present day situation of the, okay, let's say virus fear. Let's say we are a very ethical and compassionate group and we will share money with whoever who has less. Okay, at least the ones who are nearby. It's like high thermal conductivity, ready to pass on or receive heat. So at any point of time, I get money from my left neighbor if he has more than me, right? This is equivalent to thermal conductivity times to temperature difference. If I have much less than him, he will give me more. Okay. That is, if the ethical value or the thermal conductivity is good, he will give. Now, same thing I do with a neighbor on the right. Either I get it from him or give it to him. The net is difference between the two exchanges. In mathematics, the difference of thermal gradient are simply the second differential of temperature with respect to distant times is the thermal conductivity. Okay. Now, that is what is given in this picture here. The left face, let's say the cylinder is the volume we are looking at. The left face gives heat, okay, with reference to what's the thermal difference? Temperature 1 minus temperature 2 divided by small distance multiplied by area for a given time is equal to, okay, dt by dx into A. In mathematics, it is written as partial differential. Face left is same thing. Now, what does the fellow in the center the cylinder has? Difference between this and that, which we call as the second differential, okay, which is what is the famous Fourier equation. Now, back to me. I have so much of more money now. Given my nature, I can show off by buying a new shirt or a tie or keep the money quietly. Nobody knows that I have. This is like what happens if you give the same amount of heat to two material of different specific heat. Copper will show off by raising its temperature more than iron. Water has the highest specific heat and will not show off. It doesn't show. So if you have more specific heat, you won't show off. You won't raise your temperature. Okay. So if you don't raise your temperature, or if you don't show off, you continue to get the money or the heat from the neighbor. Okay. This is the beautiful thing. So what you do with your heat which you got over a period of time, okay, you use it for raising your own temperature or raising your own status. So the equation is written in a beautiful way, which is, okay, the last one you have to see, because all the others we have see alpha k by rho Cp into d square t by dx square is equal to the k by, I'm sorry, dt by dt. The increase in temperature is equal to thermal conductivity divided by density and specific heat multiplied by the second differential spatial, let's say differential of temperature with respect to space. This is what example. Okay. This is figuratively it shows. We said two neighbors left and right. You have front and back. You have top and bottom also. So this is what you see from this equation. So, friends, what happens in conduction heat transfer? When liquid metal is poured into the mold, ideally the temperature should be uniform throughout the mold cavity, but it may not be. The last entry of the metal near the downspout is hotter. The first metal has gone into the end. So that is cooler. Plus, you have the heat transfer from the mold walls. All the mold walls try to take the heat. So, solidification or heat transfer takes place from the end. And finally, over a period of time, the cooling takes place at every point of the liquid metal. Okay, every point of liquid metal, the cooling takes place. And when they reach a particular temperature called the transition temperature or phase transformation temperature of liquid to solid, they become solid. In the pure metals, it's one single point, like water, it is 0 degrees centigrade, or copper, it is 1083, like that. And then, or if it is an alloy, like say a copper-based alloy with copper, tin, zinc, lead, and all that, there is a range. It can be even up to 60 to 100 degrees. In the case of ductile iron, it's about 60 degrees. Or a range, it solidifies, okay? Or the heat is transferred, let's take up to that level. That heat has to be taken out to the molting box. Now, here the trick happens. Between the casting and the molding box, a small air gap forms, a very small air gap. Okay? And there, the minute you talk about an air gap, there is no conduction heat transfer. There is what is called as a convection heat transfer. So convection heat transfers are governed by heat transfer coefficient multiplied by the temperature difference. Heat transfer coefficient itself depends on the temperature of the air or whatever gaseous medium you have, and humidity and such factors. So depending on this heat transfer coefficient, heat is lost from the casting to the air gap. From the air gap, again, it goes to the mold. Now, people say that it's a very temporary phase, and after some time, the air gap closes, but it does happen. In the case of die casting, the air gap is more persistent, so it stays for a little longer than in the sand castings. Okay. Now, I'm talking about this because the simulation software we have today in many places in India and in the world addresses this air gap in a very minimal way, because the mathematics is not very clear. What is the thickness of the air gap which is formed is not very clear, let alone the heat transfer coefficient in the air gap. Both are not very clear. So, however insignificant this may seem to be, it is not complete without addressing the air gap, especially when you are dealing with die castings. Uh, So air gap is not addressed properly, but in traditional mathematics, we try to have done this. In fact, we addressed it at the Institute of Science way back in 1967 to 69. We addressed, some of us students at that time, we addressed the air gap formation of the castings and how the heat transfer takes place there. Okay. Now, from there, the heat goes to the molding box. Molding box is metal, so it takes away all the heat. Some of the heat is still retained in the sand, but we must know that when the casting comes down to room temperature, the sand is also more or less room temperature. If you talk about a very heavy casting, it may take 3 to 5 days. If you talk about green sand, it may take only a few hours. And when you talk about a very, very small investment casting, it may take only a few minutes. But the entire heat from the liquid metal, which you poured it at 1400 degrees or 1600 degrees in the case of steels, finally it is carried in the mold and dissipated outside the mold to the molding box. And if it's a fluxless molding, it comes out to the atmosphere. From molding box to the atmosphere, or from fluxless mold to the atmosphere, it is again convection heat transfer, okay, and governed by the same principal rules of temperature difference multiplied by what you call heat transfer coefficient. Now, it's a very, very big question mark. We addressed this in one of the WhatsApp chat group. There are endless discussions going on, and I would think, and to my very modest background on what you call simulation software in India, and when I was in BCRI, we sort of conducted a comparative study, which I told last time. They also came back to the same conclusion. The convection from the molding box or the fluxless mold to the atmosphere is least addressed in simulation software. Now, this is not to undermine the ability of the people who are working in the software. No, it is not to undermine them, because even the mathematics is very clear, temperature difference multiplied by let's say the heat transfer coefficient. But the trick is, what's the temperature difference? If you put another hot mold immediately next to this, it's very hot. And I have known in my own experience, I think I've repeated maybe in this group or some other group, I've seen some very major foundries coming into difficulty, not in the initial period because they pour very little castings, but over a period of time when they reach the near capacity, okay, of the project, they pour huge number of castings and they don't solidify as you want, because you want castings to sort of to be in liquid state till it is full and then you want to solidify fast. No, the sand doesn't understand that, and it does not give away the heat to the neighboring atmosphere because its neighbor is not atmosphere. Very closely another mold is sitting there with almost the same temperature, and hence we have problems of foundries not reaching the capacity production for this very trivial reason. They may have enough melting capacity, they may have enough let's say working men, they will have enough wherewithal to produce large amount of castings, but they have no place. They have no place to cool the mold. So they try to move the mold from one place to the other, and often they do it at the liquid state, which can hamper the solidification very much. And some people have tried putting one mold over the other, which is disastrous. And some people have even tried water cooling of molds. Then what do you do with that water? No, because sand cannot be with water. You have to remove the water from the sand before recycling. So all I would say at this point of time for people, a lot of you are using simulation software here. If there, I know there are one or two software. One person from East Europe said there are certain software which addresses what you call this convection heat transfer. So I asked him, I asked all of you, you must know what match they're using. If they're using thumb rules, then it's not good enough. Then I can live without thumb rules. If that's a good match, I understand, Foundryman. It is not necessary or not possible always for you to understand mathematics or physics of heat transfer. But you must know that you have rested your problem on able hands. You must know that, or you must be convinced that he understands. The people who have written this software they understand. When you go to a doctor, when he talks the lingo of medical profession, it's not necessary you should understand what he says, but it's very important that you know that he has understood what he's talking about. Am I right? The doctor should know what he's talking about. The simulation software people should know what they're talking about. They cannot be just a salesman pushing their product and say, okay, my software does this. It's not done. Okay. Now, one of the very able foundryman, maybe he's here from Coimbatore, he says there is one roundabout way of doing it. You can enclose every mold in a virtual doom, virtual doom, and say that between the casting and the mold and the virtual doom, you have a given condition. But who has measured that condition? You have not measured the temperature. So I'm saying that many foundries do not face this problem because hardly they reach the capacity production. Once they reach the capacity production, then they find this can be the biggest bottleneck. And there is nothing they can do about it because they built a road all around and they have limited space. They have bought so much of acreage of land. There is nothing more they can do about it. And hence they cannot reach the planned production. And if they cannot reach the planned production, they cannot reach the planned, return on investment and the profit before taxes or whatever have. So this is one thing which we need to be very, very careful about. During solidification, latent heat applies special conditions in that there is no drop in temperature till the latent heat is lost in the element. Now, this looks very simple. So you may ask, what's so great about it? You must understand that by the classical definition of latent heat, if you read any school book, it will say latent heat is that amount of energy which is required to convert from one state to the other without any change in temperature. Now, it's extremely difficult in simulation software to handle this situation because all the latent heat is handled in simulation software by what they call as equivalent specific heat. Now, this equivalent specific heat works Okay, when the numerator is a finite number. If it is a 10 by this, it works, but if it is 0 by this, it doesn't work. And the amount of heat, the temperature difference at that point, D2 minus D2, dt, D1 minus D2 is 0. It is not 6 degrees, it is not 10 degrees. So in the case of pure metals, it's very difficult. So this is another thing which is pretty difficult to handle. And yeah, there are some few research papers who handle this latent heat properly. And if anybody wants very specific uh, in a sort of questions, I'll be there to handle. Okay, now let us talk about the riser sleeves. Now we have started with the liquid to solid state. When that happens, there's a cavity in the mold, and it may not necessarily be in the center. It can be somewhere, here and there. And finally, by proper directional solidification, you bring it towards one end, and you try to place a riser there. Now, the riser can be a sand riser. Just keep the diameter of that cylinder or whatever shape you want bigger than the hot spot, or the modulus of the riser should be at least 1.2 times that of the casting. Now, it may appear very empirical because this 1.2 times gives you enough taper. I will show you one sketch a little later that tells you why this 1.2, it is there. We'll come to that a little later. Yeah, 1.2 times. Yeah, so you can provide a sand riser. Now, if you take a steel casting, like a very simple cube, okay, you will find if you keep a sand riser by going through the formula, which we said a little before, I'll go to that. Ah, you come to this mass transfer requirement. Volume of feeder multiplied by the feeder efficiency is equal to alpha. Alpha is the volumetric shrinkage of the metal which you're handling, which is the volume of feeder plus volume of casting. If you find alpha is 9%, okay, and riser, a sand riser, cannot give more than 18%. The Ladover gives, it's a very old book, but still he talks about, if you take the conical shape of the riser, then it is only about 18%. If that is 18%, and if this is 9%, you'll find VF is equal to VC. Can I come again? Epsilon is 18%. If alpha is 9%, then VF should be equal to VC. So that means the volume of riser should be equal to volume of casting. If it's a very simple cube, or if it's a very simple, let's say, sphere, when, or a casting which is chunky without any shape difference. Let's say you are trying to pour let's say a surface table, Okay. Luckily, you are pouring surface table in iron or ductile iron. Suppose you are wanting to pour that shape into a steel casting. A lot of people pour that type of a steel casting for billets and all. Now, it has got shrinkage in the center, and the entire casting shrinkage comes to the center. If somebody takes trouble of measuring that volume, it could be about 9%. And your riser is no different than the same liquid metal, which is again 9%. You will find the yield in this case is exactly 50%. Now, do you want a 50% yield? No. So what you want to do is the efficiency of epsilon of VF, you want to increase it from 18% to much higher. That's what the insulating sleeves and exothermic sleeves do. I'll show you the epsilon here. Okay, I think the cursor, yes, the cursor is, I'm not able to, but it doesn't matter, you can see that epsilon. Okay. Insulating sleeve is what? Sand is an insulator, which is good enough. Insulating sleeve is slightly better than the sand. You keep insulating material like a grain husk. In the earlier days, when I was working in a steel foundry in south of Bangalore, the person used to take the ragi husk. Karnataka is full of ragi fields. Ragi husk, and without moisture, he used to pound it and mix it with some sort of a binder and make a sleeve and give. Now, the ragi husk has got a lot of air packets, are highly insulating in nature, and they provide insulation like a thermos. And incidentally, the ragi husk also burns, and it can give enough some amount of heat. So it is not purely insulating; it's insulating with some amount of heat. Now, people have gone for several alteration to this, like paper bagasse. I used to go to the paper plants, and they throw away the paper bagasse in the manufacture of paper. They get bagasse, sort of sugar cane when they grind it and they use it. Or let's say even the sugar mills will get a lot of bagasse. Bring it here, grind it to the extent which is possible, and with a binder, you make sleeves yourself. And paper is also cellulose. That also burns. The extreme case was my own metallurgist. I don't want to name people here. He said, why not we use cow dung powder? So we used to engage people who used to make a cow dung cakes or buy cow dung cakes, grind them into powder, and make sleeves out of it. The beauty is it's extremely good because you know that it is used even to burn human bodies. In crematorium, they use that because the simmer, they don't burn like that. They keep on simmering overnight. You will find them simmering next morning. And even if there's a small rain or a shower, they don't get put off, they keep on burning. So people have made insulating sleeves with what you call even a cow dung cake, paper bagasse, or let's say the grain husk, ragi husk, or rice husk, or wheat husk, something like that. Now, the extreme case is a purely insulating material without any burning tendency. Now, we used to import sleeves. In those days, Fosico used to import insulating material from England, and that was called K-wool, potash wool. Okay, potash wool. And they are, like popcorn, not even popcorn. You go to the exhibition, you find people selling it to children. Candy, you put sugar and it expands in a big way, blown up. In fact, that's how your bone vita and many of the things are made, blown up into powder. Like that, or let's say stone. If you go to the Mediterranean, I used to work in a place called Malta, you got the blown sand, which is used in foundries, which is called perlite. In fact, you buy that, okay, commercial people give a color to that green color or a blue color, and then you put it on the top of the liquid metal, it doesn't solidify easily, popped. So there is air inside. Like that potash wool is a potassium oxide, K2O. You blow it and make it as a very fiber-like thing, and then you compress it moderately. Now, the beauty of that is this doesn't burn. If it doesn't burn, there is no carbon in it. When there is no carbon, the riser metal does not increase in the carbon content or any of the contaminants. So ideally suited for stainless steel castings because your riser composition is same as your casting composition. If you want O8 carbon, if you're aiming at O7 carbon, the riser has O7 carbon exactly like casting. So this is the beauty of what you call a purely insulating sleeve. Now you can make your own sleeve, like you can buy K-wool, potash wool, and you can make it yourself. But K-wool was the ideal at those. They're very expensive. Right. Now, what are exothermic sleeves? Exothermic sleeves at a given temperature, it gives enormous amount of heat. Now, how do you get that? The traditional practice is called the thermit process. The thermit process is uh, aluminum powder, very, very fine powder, plus iron oxide. If you put two and give some sort of initiation of oxygen by potassium nitrate or a chlorate, okay, and slightly ignite it, this catches fire. Now, this is banned in fireworks nowadays. You cannot do that, but earlier days it was. In fact, they used to use magnesium powder, forget aluminum. Aluminum is used to some extent now, but I think magnesium is totally, but I'm sorry, aluminum they use. This is called the thermit process. It gives enormous amount of energy. Now, in the olden days, they used to have this process for joining the rails in countryside or in the forest where you can't take your welding machine, there is no electricity power. So between the two rails, they used to put this thermite powder and ignite it. The whole thing will give enormous amount of it. Plus, it gives pure iron because AIL plus Fe2O3 or Fe3O4 or FeO becomes aluminum oxide. Okay, Al2O3 plus pure iron. This pure iron encourages you to weld the rails, but here we are not looking at it. In fact, in the exothermic sleeves, it actually dilutes the liquid metal which is there in the sleeve. A very good exothermic sleeve will dilute the riser metal by so much of iron, which is not harmful at all. You need to, I mean, it is not lost. But the problem is they may use a lot of burning material like a feldspar or a fluorspar. I'll tell you why the feldspar or a fluorspar is used. Okay. Now, this is what is exothermic sleeve. There are so many variants of that. Now, the trick is the aluminum powder in the dust form is extremely costly. So people don't use pure aluminum powder. They may use aluminum chips, some coarse powder, and then very small quantity of fine powder. Doesn't matter if it catches, and in one way it's good, it will delay, the sort of burning, what they call as a sustained release. You have got tablets of vitamin and all that sustained release like that. The heat will be sustained and given over a period of time. So you can use that. Now, the problem is some people use fluorine-based material in what you call exothermic sleeves. Now, fluorine is a deadly poison and not allowed in many countries. Now, what does fluorine do? The thermal process, aluminum acts with iron oxide and takes away the oxygen and becomes aluminum oxide because it has got a very low free energy requirement. It's like snatching a lover from iron. So it snatches the lover from iron oxide and takes it away, elopes, right? After some time, aluminum is lost. It is not available for further. I think you require about 23% or something if you do the correct equilibrium to draw. So what the people use is they use fluorine. So what does fluorine do? Fluorine acts with aluminum oxide and takes away oxygen from aluminum oxide because it's one of the most powerful antioxidants. That's a deadly poison. Fluorine, if you inhale, you are finished because it takes away oxygen from every pore of your body. Now, nothing wrong from our angle. Castings have no life, but if it can get into the hands of people, fluorine can be dangerous. Now, slightly digressing, you got some toothpaste in India which use monosodium fluoride for toothpaste so that they can clear the tartar, remove the tartar is some sort of an oxide, calcium oxide plus silicon oxide and all that. They remove the oxygen, free the tartar, but it's good, but in limited quantity, but in larger quantity. So in many parts of the world, even in toothpaste, fluorine is not allowed. I know companies in South India where because of fluorine in that particular area, uh, people have lost life and companies had to close down near Coimbatore area. This has happened. So be careful with fluorine. And why I'm saying all this is try to educate the supplier that let's not do anything in India which their own parents' company do not do in the Western countries like England or America. A new concept has come in the last few years. It's called Niyama criterion. I wouldn't say last a few years. I would say when compared to the history of simulation software, halfway through, about 15, 20 years back, it came. It's called Niyama criterion. Now, I want you to don't look at this particular picture. Look at from another angle. If you want castings to solidify, you want temperature difference, which is called a thermal gradient. There should be a thermal gradient, temperature difference divided by space is called thermal gradient, which is important for heat transfer. Okay, but the casting itself should not become cool because then it won't attract liquid metal easily. So this ratio G by root R G is thermal gradient, R is the cooling rate, G by root R is okay is called the Niyama criterion, and one should plot this Niyama criterion at every point of the casting. Many of the simulation software deal with 1 minute, hold on. Okay. Many of the simulation software deal with Niyama criterion, and it tells you what is the Niyama criterion at different points of. So you must draw the Niyama criterion, and textbooks say that it should be 1.2 to 1.5 in the case of steel casting, or should be zero point 0.8 in the case of ductile iron casting. Come to your own conclusions and find out what is ideal for that. And literature, I find that I like to keep Niyama criterion in the entire casting as 1. Now, many of the users of Niyama criterion, they say they have no use for Niyama criterion. It is too theoretical and it is not. Well, I consider it as one of the very important aspects to find micro shrinkages. We are not talking about macro shrinkages because everything is fine. There is a feed metal channel, liquid metal is available to feed the hot spot, but then the casting is solidified too fast, and hence it is not able to take even the liquid metal which is coming. Let's say you want money or you want help, but there is somebody which is very close to you to give the help or the money, but you are closing the door. Then they can't do that, like that. Okay, let's get back to. Hmm. This is a picture taken from the John Campbell book Castings. It says different types of what you call shrinkages. You see a casting and a riser on the left. Okay. Now, this is called liquid feeding, this area, liquid feeding. This one is called mass feeding. That is, the liquid has become small pieces of metal, small pieces. Where is that cursor? Okay. Now, this has become small pieces of liquid has become a little solid there, little solid. Now, interdendritic feeding is the most difficult because dendrite has started forming, that is, like fruit trees, the growth has started from the side of the casing. There, it is very, very difficult to feed, and that is called interdendritic feeding. Now, burst feeding is because of the hydrostatic pressure, suddenly there is a burst and it starts feeding on this. Now, we don't expect a result from bus feeding and design a casting like that. We depend purely on liquid feeding, mass feeding, and then interdendritic feeding. Now, this slope is very important, which is about 20%. That's why you want the modulus of the riser to be 20% more than the modulus of the casting, which I've discussed again and again. Okay. One word about chills. Now, what are chills? Now, mold is a highly insulating material. So if you want to have a casting with a different cross section and if you want to still feed it, you would like solidification to be faster in a few places. So you provide chill. Suppose you're pouring a casting and the casting suddenly has a boss. Whenever there is a drill hole, a small boss is given by the designer. And finally, he's going to drill a hole there, but which you cannot put a core, it is too small. So the section suddenly becomes heavier. So you have to put a little bit of a chill there. Okay. So chills extract heat much faster and hence it improves the direction solidification. There are a few things about chills. If you're having cast iron, you can straight away use a cast iron chill, or you can use a steel chill, or you can use a silicon carbide chill. You can use any one of that. Okay. Now, one thing is very important. When you pour a metal, the metal has got lot of dissolved gases, and the dissolved gases have a certain miscibility in solid, so they try to come out. For example, you take a Coca-Cola or any soft drink, when you increase the temperature or when you drink those in a room temperature, they do not taste well because so much of carbon dioxide they put in, they're all in dissolved form. It just goes. Whereas when you it's cooled sufficiently, near the freezing temperature, all these gases are trying to come out of the liquid, okay, and hence give you the tingling of carbon dioxide in your mouth and the throat. Like that, when liquid metal solidifies, it cannot contain all the gases and they have to come out. When they come out, they can go through the permeability of the mold, or through the casting itself, they can go back. Very unlikely. So they depend on the permeability of the mold. Well, instead of mold, if you got a chill, where is the permeability? So you got what is called as a chill blow. Many times you will find chill blow, even if you have nicely ground the chill, when there is no iron oxide or rust in the chill, still you will find there is a lot of chill blow. Another reason for the chill blow is if the chill is uh, rusted, you put a steel chill, you take a sheet metal or a small steel piece and then use it as a chill. Overnight it rusts. Rust is nothing but iron oxide. Iron oxide is very porous in water form, FeO, Fe23 or Fe3O4. It's very porous, and hence it has got a lot of air inside. That is why they say that if you meet with a small piercing of your leg or an accident on the roadside, and especially if it's a rusted material, in those days they used to say horseshoes, because horseshoes used to be left behind in those days because they're horse-drawn carts. The bacteria in a rust can stay for a longer time because it has got air and a moisture because it's porous. Now coming back to our this thing, that rust has got a lot of porosity, and that porosity can have a lot of moisture, and that can give you the chill blow. So one is to grind the chill sufficient. There's one more precaution people have found. People have put numbers. So after you use the chill once, you grind one, and if you use it twice, two, three, four. Now you keep on grinding. The reason is very simple. Not only to remove rust. When liquid metal comes into contact with chills, when liquid metal comes into contact with chills, if the chill is iron, it burns the iron flakes or it burns the iron nodules if it's a ductile ion chill. Now that is a gap. When next time when you use the chill, the liquid metal cannot go into the small crevices of what you call graphite, which is already taken in those places. It cannot. For example, if you see a microstructure, gentlemen, you are not seeing graphite in iron. What you see is where graphite was there before. In polishing operation, the graphite goes. Similarly, when you use a chill, when you pour a casting, the graphite flake goes away or burns away. So next time there's a small crevice there, the air entrapped there becomes a blow. So these are the reasons why chills give you blow. So people have done, I have seen one foundry cutting grooves in chills. When you cut a groove in chill, the air or gas which is produced in the nearby, you are giving a way for it to escape, and life is comfortable. So that's one way of doing it. Okay, right. We're not dealing with filters here. Yes, Calpor is one thing which is a filter come riser. Some manufacturers give you. So you pour right on the top of the casting. It comes in the fluid mechanics like last Friday, whatever we covered. You pour right on the top of it. And then the filter is there to prevent all the slag and dross. And after some time, the filter floats and the riser neck is very convenient for you, and you are done with it. Ah, liquid shrinkage, solidification shrinkage. When the mold bulges, the shrinkage goes deeper, as you see here. Very fundamental. I think it's taken from ASM, I think, whatever it is. Gentlemen, I think we have come to the conclusion of this presentation. My conclusion on this webinar, or any webinar for that matter, where there is a lot of science, very little room for art, I say that science and nature is very punishing, as it's punishing all of us right now. You know what I'm talking about. I do not even want to use the word here. It's not willing to cooperate, unlike humans, with those who approximate and do shoddy work. It doesn't. It has its own rules. You drop a stone, it drops, finished. There's nothing, oh, I made a mistake, let it not fall down. Mere experience can be highly misleading. You have to go into the analytics, the principles of all this at any point of time. Okay. And last, the hallmark of good experience is to gradually understand, and more importantly, to explain to ourselves why things work in a particular way rather than how things work that way.